Hello, everyone, and welcome to the European Non-Associative Algebra seminar. It is my pleasure to introduce our today's speaker, Lucia Bagnoli from Sapienza University of Rome. She'll talk about some new classes of quantum vertex algebras. Please.
Thank you for introduction. I'm going to share the screen. Let me just put it in full screen. Okay, I hope that you can see now. Thank you for the organizers for the invitation, and in this talk I will present some results on new families of quantum vertex algebras, and it is based on two works, one with Slaven Kožić and one with Marijana Butorac and Slaven Kožić. The outline of the talk is more or less divided into three parts. The first one will be dedicated to recalling some notions, definitions, preliminaries on quantum vertex algebras. In the second part, I will move to the first series of results that are those obtained together with Slaven in the rational case. So we present a new class of quantum vertex algebras that we introduced in the rational case, and the final part of the talk will be dedicated to the last results obtained together with Marijana and Slaven on a new class of quantum vertex algebras associated with the trigonometric matrix. So, since I have to recall what is a quantum vertex algebra, I want to start before by recalling the definition of a vertex algebra so that we can compare it to that of quantum vertex algebras. So, vertex algebra V is the datum of a vector space over the complex field for us, in which we have a special vector that is the bold one called the vacuum vector. And we have an endomorphism T and a vertex operator map Y. And they satisfy a list of properties in which the most important one is what is called locality. That is the third one in this slide. And we will compare it to that I will present in the quantum vertex algebra environment. But before recalling what quantum vertex algebra is, let me set some notation for the following. Let me also recall that the problem of associating vertex algebra structures to quantum groups was posed by Frankel and Jing. And in the following, the setting will be this. We will consider H to be a formal parameter, and we will consider modules over the ring of formal power series over H, C of H. And I recall that V is said to be topologically free when it is isomorphic to V0 of H for some vector space V0, and it is known to be equivalent to ask that it is torsion-free, separated, and complete with respect to the Chadic topology. In the following, we will use also this notation. Given a V that is a topologically free C of H module, we will denote by this symbol, V of Z subscript H, the series such that the coefficients with respect to the Chadic topology go to 0 for R that goes to infinity. And given this, I'm able to recall the definition of Fettig Kashdan for quantum vertex algebras. It is a quite long definition, so you see that this is only the first slide because I have a second slide for the definition. But I won't go on into the details of all the steps of the definition. I will only emphasize the most important properties. First, the big difference between the quantum vertex algebra and the vertex algebra is that here we have an extra ingredient that is this curly S, that is the so-called braiding map. Indeed, again, we have here a vertex operator map that now goes to V of Z H. And this braiding map has a some list of properties. The first one is that for H that goes to 0, we recover the identity. And it satisfies the Yang-Basser equation. And the most important property of quantum vertex algebra is the deformation of locality, that is the so-called S-locality, which is this one. It is actually very similar to the locality, but we have a deformation by this braiding map S. Let me say that people used slightly different definitions of quantum vertex algebra since last years. For example, Aishan Lee didn't consider this requirement, so that for H that goes to 0, he recovers something that is slight generalization of vertex algebras. But in this talk, we will stick to the definition introduced by Atigo Venkashdan. So in their paper in 98, they gave this definition, and also they constructed the first examples of quantum vertex algebras that I want to recall, so that we can compare it to what we obtained. But in order to recall how they constructed the first examples of quantum vertex algebras, I needed to recall some preliminary definitions. That is the one for the double Yangian of type A. So let me set for the following some notation. We will consider the tensor product of the endomorphism of Cn times itself. And in this space, we will consider two matrices, the identity and the permutation matrix. And of course, I recall which, because we need it, the Yangian matrix that is defined by this formula. It is well known that it satisfies a Yang-Basser equation, and that it is possible to normalize it with a function f, in which for which I don't want to go into details on how it is constructed, but it is possible to renormalize it so that it also satisfies the unitarity property. And I recalled the Yangian matrix because I wanted to recall the double Yangian for type A. Because we will see that it was used to construct first examples of quantum vertex algebras. So let me recall how it is defined. The double Yangian for GLN is defined as the genetically complete associative algebra over C of H, which is generated by a set of generators, that is the central element C, and these guys, Tj plus or minus R, subject to some relations. It is possible actually to give the relations explicitly between these guys, but what in practice is more convenient is to organize this Tj plus or minus R into some series, and then organize the series in some matrices, and then reformulate the relations between the generators into matrix relations. So what is usually done is to take this Tj plus or minus R, organize them into series like these two, T minus and Tj minus and Tj plus, and then introduce two matrices, T minus and T plus. So that the relations can be given in these compact formulas that are the so-called RTT. It is called RTT presentation, and with this subscript, that means that, for example, if we consider T1, means that the EIJ of the matrix T is in the first tensor factor, and in the second one we have the identity. And similarly for T2, we have the EIJ in the second one. So, of course, the Yangian and dual Yangian can be seen inside this double Yangian that in some sense condenses in one structure these two structures. The Yangian is spanned by by the TJR with the positive R, and the dual Yangian the TJ minus R. And it was proved by Jean Kožić, Molev and Yang, a PBW theorem for this double Yangian. And in the following, we will call double Yangian at level C for a complex C. The quotient of the double Yangian by the two-sided ideal generated by C minus C. And the main ingredient for the Atticon-Kazan constructor was the so-called vacuum module, denoted by this symbol, which is the quotient of the double Yangian at level C over the left ideal generated by the element stage AR with positive R, which means that actually as C of H modules, this vacuum module is isomorphic to the dual Yangian. So we have now the main ingredients to recall how they constructed the first examples of quantum vertex algebra. So we just need some further notation. So if we consider this tensor product in which the first tensor is that actually the tensor product of n copies, small n copies of the endomorphism of Cn, and the second one is m copies of the endomorphism of Cn times itself. We consider set of variables u and v, where u is a compact way to consider the variables from 1 to n, and v a compact way for considering the variables from v1 to vm. And I need to introduce some notation that in some sense is useful because it is a compact notation for some products that appear in the formulas. This notation is only to consider a product of R matrices in a more compact way, where these arrows in the products means gives us the direction in which the products are taken, and this t subscript square n is only a compact way to denote the multiplication of t1 plus or minus to tn plus or minus. So this notation I needed to recall this, that is actually the result by Atticon-Kazan of 98, in which they constructed a quantum vertex algebra structure over the vacuum module. So they proved that for any complex C, there exists a unique quantum vertex algebra structure over the vacuum module for Gelen. And they gave it explicitly because they gave the explicit expression for the vertex operator map and the explicit expression for the braiding map. Apart from the details of how these maps are defined, let me give you some history about what was done on quantum vertex algebra since the last years. So I said that Atticon-Kazan introduced them in 98, and they gave the first examples. I recalled this one is the one associated in type A with the rational R matrix, so that is the Yangian matrix. But actually, the constructed in type A is also associated with the rational trigonometric and elliptic R matrices. Later, Butorac, and Kožić, then Kožić, constructed new examples of quantum vertex algebra associated with rational and trigonometric cases in BCD. And they followed the Atticon-Kazan construction. What happens in all these cases is actually that the S-locality turns out to have a particular form that is already appeared in literature. It is the so-called quantum current commutation relation that is in practice some sort of this relation in which the R is the R matrix that we're considering, and this curly L are the matrix operators depending on the specific example. And also I want to say that in the last years many people studied quantum vertex algebras. For example, the Solegardini and Cass studied structure theory of it, and there are also some other results by Jin Litan and Kong and others. What actually motivated us for the results that I will present is actually that we were wondering if it was possible to construct non-trivial examples of quantum vertex algebras for which the S-locality has a different form. And so we did it first in the rational case of type A with Slaven, and then we generalized it to the trigonometric and elliptic case of type A with Marijana and Slaven. So I first will present the rational case. And let me say first that our approach was to, in some sense, follow the Ethical construction for which they used the double Yangian. So we, in some sense, tried to mimic this technique. Of course, we couldn't use the double Yangian for GLN because we wanted a different structure. So we took again in the rational case the Yangian matrix. We consider for technical reasons two normalizations of that we called in the following R bar to refer to both of them when we want to refer to them actually. And the first ingredient that we needed was something that in some sense plays a role of what the dual Yangian played in the construction. So something on which we will construct the quantum vertex algebra structure, so that we introduce this that we call the AFR bar, that is an algebra, of course, over of H that is generated by this Lij minus R, with R from 1 to infinity, and again we organize them into a series and then in a matrix, and we impose that they were related with this RLL relation. Since we wanted to follow the ethical construction, they use the double Yangian, as I said. We needed some sort of structure that mimics as double Yangian for our case, and so we introduced this D of R bar algebra, which combines in itself the A of R bar algebra that we introduced and the Yangian, so that it is a deformation by the Yangian of our A of R bar. Indeed, it is generated by a series of elements, Lij R with R that is now in Z, and the Lij minus R are related, are organized in Z plus minus, and are related with this relation that is the same of A of R bar. And for the Yangian elements, they are organized as usual in the Lij minus of U series, and then in L minus, and given the relation of the Yangian, and then we have the mixed relation that combines L plus and L minus. First, we proved that actually over our A of R bar there is an action of D of R bar. Of course, the action of the L plus matrices was just the multiplication by on the left, and the action of L minus instead is given by multiplication by some R matrices, and indeed it is quite similar to what happened for the double Yangian. And in particular, it is possible to prove that the action of L minus belongs to this tensor product in which we have on the right the homomorphisms from A of R bar to A of R bar of U minus 1 subscript H. That means that with respect to the Chadic topology, it is a polynomial in U2 minus 1. Actually, this is what is the usual definition of restricted modules. Indeed, given W a module over D of R bar, it is said to be restricted when it is a topologically free C of H module, and L minus the action of L minus belongs to this tensor product. And of course, an example of it is A of R bar. Now, The main result was that we were able to give to this guy, A of R bar, the structure of a quantum vertex algebra. And in order to do it, actually we needed to define the vertex operator map and the braiding map explicitly. And now I reported here the definition, the expression that we use. It's not really important that we go into the details. These TIs are just transpositions, and actually this is actually not the explicit, not the general formula for our braiding is only a particular case, but we are not really interested in these formulas. It's only to say that we have explicitly the quantum vertex algebra structure on over this guy. And what I want to point out is that if we look at the vertex operator map for n equals to 1, we obtain an operator that we call L of u. And actually it is possible to prove using the properties of our D of R bar that it satisfies an RLL relation. And what happens is actually in the proof of this of the fact that it is a quantum vertex algebra, what happens that we prove that the S-locality is not anymore in the quantum current commutation relation formula, but it has it appears as an RLL formula. So it is a different type of S-locality. What we also noticed is that in our vertex operator map, we have here we have some L minus, and if we go back to the definition of L minus, this that comes from the Yangian, we have that it has a singular part. It was proved by the Solegardini and Katz that the quantum vertex algebra is S-commutative if and only if the vertex operator map doesn't have a singular part. So in our case, it is actually a not S-commutative quantum vertex algebra, where S-commutative means that the S-locality is satisfied with the R that is the power of Z1 minus Z2 that is 0. And what happens that in our case this is not S-commutative, and for h that goes to 0, this part of the vertex operator map goes to 0. So in practice, for h that goes to 0, we recover a vertex algebra that is commutative. And in practice, our structure of quantum vertex algebra is a deformation using the Yangian of this possible quantum vertex algebra structure over our A of R bar that is S-commutative because it doesn't involve the Yangian. We partially investigated also the representation theory of this quantum vertex algebra that we introduced. So let me recall what it is a module over a quantum vertex algebra. A module is a set of W and YW, that is a module map. W is the module, where W is a topological efficiency of each module, and YW is a model map that satisfies a weak associativity property. In the following, I will need this notation. I'm sorry for the notations that are quite complicated, but actually they are useful. R subscript square n means the product of these R matrices in this direction. And we were able to prove that given a restricted Diaphara-bar module, on it we have a structure of our module over our quantum vertex algebra, and we have also the explicit formula for the operator map for the module map, and we were able also to prove that. Given a model over our quantum vertex algebra, it is possible to construct an operator L such that satisfies the RLL relation. Actually, we were able to prove that it is possible over a W to give a structure of module over our quantum vertex algebra, if and only if it is possible to construct on it an operator L that satisfies the RLL relation. And this was also we were able also to generalize this result in the trigonometric case that I will talk about later. We wanted to investigate also something about our braiding map S. So in order to do that, we needed some results on some results that is called fusion procedure. Let me set the notation and recall this result. We have, of course, an action of the symmetric group over the tensor product of n small n copies of Cn times itself, and we will denote in the following the action of the symmetrizer and anti-symmetrizer by these two epsilon symbols. And let me recall that the fusion procedure is that says that if we take our product of our matrices and we evaluate it at some suitable U1, UN, it turns out to be a scalar multiplication of the symmetrizer and anti-symmetrizer. And in our case, since we are considering some normalization of the Yangian matrix, we get a different scalar, but it is not really important. So we considered this series, one for plus and one for minus, that are series with coefficients in our quantum vertex algebra, and they are defined as a trace over the factors from 1 to n of these products. We were able to prove that actually they are fixed points of the braiding. And I wanted I recall the fusion procedure because in order to do that, actually this was the main ingredient. And also in the case of the anti-symmetrizer, there is a slight more stronger result because of a property that the anti-symmetrizer has, but okay, this is not so important now. And this fixed point of the braidings, we noticed that they had some sense, a link to an algebra that was introduced by Krylov and Rybnikov. Indeed, Krylov and Rybnikov were interested in studied anti-dominant shifted Yangians, and in their work they introduced a sort of generalization of the Yangian, that now I recall, and we noticed that since in their work they constructed some commutative families in this algebra, we noticed that there is a link between these commutative families that they obtained our fixed points of the braiding. Let me recall the definition of what the algebra that they introduced, even if we slightly modified it to work over C of H so that it fits the quantum vertex algebras environment. So they took this algebra Y that is generated by this lambda ijr, with R that is in Z. Now the Lij are organized in a series which involves in the series all the possible powers of U, and then they organized them into a matrix and in an RLL relation. For technical reasons, they had considered a suitable completion of it, so that they were able to define these elements, this series. Actually, they defined these series that are again defined as a trace over the tensor factor from 1 to n of the product of the anti-symmetrizer and these guys. And these have actually coefficients in the completion of their algebra, and they proved that they mutually commute. We noticed that given a module WYW over our quantum vertex algebra, actually it was possible to construct over it a structure of a module over their algebra, their Y of Ret algebra, and we were able to slightly generalize the result about the families that mutually commute to the case of also to the symmetrizer, and we noticed that actually due to this assignment, the fixed point of the braiding that we found were those that corresponded to these families of families that mutually commute. So this actually was the link that we noticed. And something similar happens also in the trigonometric case. So this is much more or less what I wanted to say about the rational case. Now I will move to the trigonometric case, in which, together with Marijana Butorac and Slaven Kožić, we tried to generalize what we did for the rational case. We started, of course, by considering now not anymore the rational Yangian matrix, but the trigonometric R matrix. I reported here its definition that is quite not as easy as the rational case, but I mean only to recall it. And what actually we used was these two are matrices that are normalization by a suitable variable g, and we consider the dependence only on one variable, and it is well known that actually this satisfies the Yang-Basser equation. In this case, the multiplicative version of it, and they satisfy also the unitarity property. Now, the approach that we used was the same as we did in the rational case, so try to mimic the Tivogov and Kasdan structure without, of course, using the double Yangian, but slightly modify the structure so that we obtain a new quantum vertex algebra for which the S-locality is in the RLL formula. So again, in this case, we introduced this V of R, that is the one that in this case plays the role that was played in the Tivogov example by the dual Yangian, so that it is the algebra on which we will give a quantum vertex algebra structure. And again, it's topologically free associative algebra over C of H, and again, is generated by elements Lij minus R, with R that goes from 1 to infinity and Ij from 1 to n, and again, they are organized as similar to what happens in the rational case in Lij plus of U series, and then in the corresponding matrix, and then, of course, the relations are given in the RLL formula. Again, the subscript 1 and 2 means that where we have to apply the EIJ, depending on 1 or 2 subscript. And this is a generalization of the rational case to the trigonometric case. We were able to construct an operator L of U in this tensor product, so the tensor product of the endomorphisms of Cn and this homomorphisms, so that it acts on our V of R in this way, and it satisfies the RLL relation. Actually, this is actually the straightforward generalization of the rational case. Indeed, we will see later that it is possible to give also the explicit action of an operator L minus that is the direct one that corresponds to L minus that we had in the rational case. Let me say that again I need here to fix some notation, which is quite similar to the one that we saw in the rational case. It's just for to make the formulas easier in some sense. So R subscript square n means that their J matrices are multiplied in these directions, and R1, 2, and M, or 1, 2, when 1, 2 has this superscript means that the arrows are reversed, and again L subscript n, L plus subscript square brackets n means the product from L1 to L, from L1 plus to Ln plus. And this L, subscript square brackets n, means this product times at the beginning the R matrix, the multiplication of R matrices. So we were able to prove this result that gives a quantum vertex algebra structure over V of R. And of course, we needed to give the explicit formula for the vertex operator map and the braiding. Here it seems slightly different from the one that we had in the rational case, but actually it is not. Indeed, it can be written again as this one with the transposition. So actually, it is the direct generalization for the trigonometric case of what we did in the rational one. And again, what happens is that the S-locality takes the form of the RLL relation for the operator L. I didn't mention before that in literature the RLL or RTT relation is also known as a FRT relation. And so probably in the following I will maybe I also used before FRT. I mean they are the same, just two different names. And we wanted also in this case to explore something about the representations here of this object. The main difference between the rational and trigonometric case is that in the trigonometric case, the definition of a module that is more convenient is this called the definition of phi coordinated modules. Phi coordinated modules were introduced by Ashen Lee in a series of papers, and they were really useful in the trigonometric case. Before recalling the definition of it, let me just recall some other notation definition. First, we were able to prove that there exists a module map, a CFH module map, a sigma, that was given by this formula. And also let me say that in the following we will call an operator over W, that is a CFH module, to be an FRT operator if it satisfies the RLL relation. So, given these two ingredients, let me just keep this slide that is quite technical. We now are able to recall the definition of phi coordinated modules introduced by Ashen Lee, and in this case, actually, we only consider the case of phi to be this expression. And phi coordinated modules, a module over V of R is a pair W by W, where the W is the module, it is a CFH module topologically free, and we have the module map Y, Y subscript W. It satisfies some properties, in particular the two important one are the weak associativity, in which actually is involved the phi, and the sigma locality, that is a locality that involves the sigma property. And we were able to prove an analogous of what happened in the case of the rational R matrix. Indeed, in the rational matrix case, we were able to prove that it was equivalent to construct on a C of H W module the structure of a module over our quantum vertex algebra if it was equivalent to construct an operator L of U such L of Z, sorry, such that it satisfied the RLL relation. And this is actually what happened also in the trigonometric case. We were able to prove that given enough RT operators, that means that satisfies the RLL relation over W, that is a C of H module, it is possible to construct over it a structure of V of R module, and on the contrary, given a module over V of R, it is possible to construct on it an operator that satisfies the FRT relation. Now, since we are going in parallel with the rational case, in the rational case, I recall that we constructed a D of R bar, we called it D of R bar algebra that combined in one structure the algebra, the Yangian and the algebra that was what we call the A of R bar, that was the one that we use instead of the dual Yangian. And here it is possible again to combine our VFR and in a sort of double construction. So we consider this DFR algebra that is again generated by the elements lambda ij plus or minus r, subject to the relations that are involved in these compact formulas. Again, we have to organize the Lij plus or minus r into two series and again to two matrices, and they are obtained, the relations are organized in this compact matrix formulas. Again, here inside this DFR, it is possible to see some sort of generalization of the Yangian that is called the H Yangian, which is generated by the elements lambda ijr, with that are actually encoded in the L minus matrix. And again, we will call in this case a W module over D of R to be restricted if the action of L minus belongs to this tensor product, similar to what we did in the rational case. So we were able to prove again that also in this case as well, given a restricted DFR module W, it is possible to construct over it a structure of a VFR module, facultated VFR module. And I said before that we found a link between the fixed points of the braiding in the rational case and some commutative families inside an algebra that was introduced by Krylov and Rybnikov, that in some sense generalize the Yangian, and the same happens in the trigonometric case. Indeed, it is possible to construct a sort of generalized Yangian that in some sense is the trigonometric version of the algebra introduced by Krylov and Rybnikov in the rational case. Indeed, it is generated by TAJR elements which are in Z that are now again encoded in a series which has that the powers of Z are all the integers, and again they are organized in a matrix curly T, and in an RTT relation where this R is the trigonometric matrix, and again, it is possible to say that a module over this generalized Yangian is restricted if again the action of this tau is curly T is belongs to this tensor product, and similarly to what we obtained in the trigonometry in the rational case, it happens that given a module of our quantum vertex algebra phi of R, frequented module, it is possible to construct over it a module over this generalized Yangian. And again, it is possible, without going into the details, to construct a suitable completion of this generalized Yangian, so that it is possible, to define in the series in the middle of these slides, which are actually the trigonometric counterpart of those used by Krylov and Rybnikov. Here, this is actually the action of the antisymmetrizer in the trigonometric case, and this actually mutually commute, and we were able to see that they again are linked to fixed points of the braiding, sorry, not of the braiding, of our sigma, in our case as well, in the trigonometric case as well, because we were able to construct this series that are similar to the cases in the rational case, and again the fixed point of sigma, and again in using this assignment, it is possible to see that actually the points, the fixed point of sigma are those that correspond to these mutually commutative families. So this was more or less what I wanted to say. I have to say only that to finish only that I omitted to speak about the elliptic case that we studied as well, but it is much more complicated, and this was already enough complicated regarding annotation, so I wanted to skip that, and so that, yes, is more or less what I wanted to say. Thank you for your attention.
All right, so thank you very much for the interesting talk. Are there any questions for the speaker? Comments? Okay, so it seems to me there are no questions. So let's thank our speaker.
Thank you.
So we look forward to seeing you all again at the same time next Monday. Thank you very much, everyone.